Hello, welcome to the 10th video of this course. So today we'll be speaking about, we'll be discussing about real and complex analytic functions, and of course the heart lies in the past series. So we'll look at more about past series, but let me define first real analytic and complex analytic functions. So complex analytic function we have already defined, we'll recall, and we'll look at some properties. Of course, in terms of past series, so real analytic function. On some domain in R and one variable. A function f from an open subset U of R to R, U is open in R, is said to be real analytic on U if for every point x naught in U there exists a positive real number R and a power series summation an x minus x naught or n from 0 to infinity with an real for all n in 0 union the natural number, so and a power series which converges on x naught minus R to x naught plus R and fx is summation n equal to 0 to infinity n x minus x naught for n on U intersection x naught minus R to x naught plus R. Alright, so you have an open set, not necessarily connected, and for every point in that open set you have positive number and a power series such that the power series converges in this interval and fx has to be equal on this. So what is this actually? Let's draw a picture. So suppose this is for a real line. Suppose U is, let's say, AB union CD. So U is AB union CD. And suppose x naught is that point. X naught. And so the point, it's saying that you have an R. Let's look at it, might be a little bigger. R, this is x naught minus R, this is x naught plus R, such that on this on this converges. Alright. So the radius of convergence of this fast series will get into bigger one. But that on the U intersection on x0 minus that R, capital R, radius of convergence, on this it might not be equal to fx. We don't need for this definition. Now complex analytic. Function let a function f from omega to C. Omega is an open subset of C is, maybe I should erase this part. U is in this case AB union CD is said to be complex analytic on omega if for every point Z0 in omega there exists R. Similarly, there exists R greater than 0 and a path series summation n z minus z0 or n in from 0 to infinity. Well, now a n can be complex number which converges on d z0 smaller and fz and satisfies fz equal to summation n from 0 to infinity an z minus z0 for n on omega intersection d z0 r. Alright, so let's look at the picture again here in this case. So suppose omega is of this kind. Suppose this is omega union of this connected couple, union of these two connected couple. And let's look at z0 right here point. Now what it says is there exists one R this is d z0 R. It might have this R bigger so that this intersects both of them, but then it has to be equal in both the intersection. But since it says there exists one is good enough, so one which does not intersect to other components, that will work for us. Alright, so the condition that intersection with other part has to be equal to f, that is not needed. So that's why we didn't put that. So 1R is good enough. So on this intersection, here the function has to be equal. this is omega intersection d z naught. Alright. Now let's look at a few examples. So example from the last time. We know last time we worked with complex variable, so in particular it works for real variable also. So you have x to the power n by factorial n, right? Which of course on whole of r, and this is nothing but exponential. Alright? Alright, so this is exponential is well, there's a problem. Exponential is real analytic. Is it true? We need proof. We need a proof because this is a past series. Let's look at it. This is summation from 0 to infinity. This is a past series around 0. What happens around the other point? Alright? So that's why question mark. We'll come to it. It needs some work. So what we can example maybe 2 is good. So fx is polynomials. In x. Alright, so polynomials should be okay because suppose you have a naught plus a1x plus an x to the power n. This is px. Around 0 you can write it a naught plus a1 times x minus x naught plus x naught and so on, plus an x minus x naught plus x naught power n. Now this, you expand this binomial, and since all are finite, you get together the constant terms first, and then in terms of x minus x naught there, and then x minus x naught square, coefficient of x minus x naught square next, and so on. So we will see this polynomials are real analytic, and so this polynomials in x are real analytic. And polynomials in Z are complex analytic. Alright, so this is what. Whatever comes next, we need a proof. Right? So, next aim is to show that a past series is real analytic in real case and complex analytic in complex case. But we need some techniques to prove it. Alright. So an exercise. So to prove that a past series in real variable is real analytic, what we need to know about the interchanging of summation. So suppose the following. We'll look at complex number itself. A, J, K belongs to N. Be a double sequence alright, and define such things such that define this Vj, or let's look at, maybe you can write Bn is j equal to 1 to n, is it just a minute. Alright, Bj, this is not Bn, what we want, Bj. Define Bj like this: k equal to 1 to infinity aj k mod. Alright, and assume summation Vj j equal to 1 to infinity converges. Alright, so define this one sequence of, from double sequence you create a single sequence, and the sum of that should converge. Then the following, then summation j equal to 1 to infinity, summation k equal to 1 to infinity mod ajk is equal to summation, then so that actually, this is an exercise, so then show that k equal to 1 to infinity, j equal to 1 to infinity, ajk. Alright, so you can interchange the summation. So those who have done measure theory course might realize this is discrete version of Frobenius theorem. Alright, so this is for all you. So we need this to prove that any convergent past series is real analytic on its domain of convergence. Theorem. So we'll do it in real case, and the complex case will be an exercise, it's just analogous, similar to that. So theorem A, past series is a real analytic in X maybe I should say convergent past series in X is a real analytic function on its domain of convergence. What does it mean? It means that given a past series n, given the power series a n x to the summation a n x to the power n, x minus a to the power n, and suppose the radius of convergence is r, then you look at a minus r to a plus r, that interval, and the point is you can express that power series in the form of x minus b, b in the interval. What does it mean? So it means, so what you need to show, maybe I'll start with a proof. Suppose n x minus x naught or n from 0 to infinity is a power series which converges on x naught minus r to x naught plus r. So you can assume r to be its radius of convergence. There is no harm in that. And suppose this, and let's b belongs to this x naught minus r to x naught plus r, x naught plus r. X naught plus r. Yeah. What you want is to show, you need to show there exists a power series, there exists r greater than 0 and a power series summation bn x minus b or n from 0 to infinity, which converges on x naught minus r to x naught plus r, and this a x minus a x minus x naught for n. This is not x naught, this is b. This is b is equal to summation bn x minus b or n on this x naught minus r to x naught plus r intersection with b minus r, b plus r. Alright? So b is in the domain of convergence of the first power series, and around b there should exist another power series which converges in some neighborhood of b which are equal on this intersection. This is what we need to show. Alright?